Here's a secret. NMR spectra are actually really easy to solve. Because of time constraints, there's a limit on the difficulty of the problems you can be asked, and about 80% of those problems can be solved with only good proton NMR skills. With a bit of carbon and IR background, you'll be impossible to stump. The key is to develop a decent algorithm that breaks down the spectra into bite-sized chunks, which are easier to manage. The one I'll be showing now evolved over about 2 months and worked well until graduate school. Start by determining the unsaturation number. This tells you how many double bonds or rings are in the system and is derived from the molecular formula, which if not provided can be determined from the molecular weight. Step 2 is to group protons by shift, identifying them as likely ethers, aromatics, alkyls, and all the rest. Pad your non-aromatic estimates on the d-shielded end to account for electron-deficient neighbors. For step 3, integrate the proton peaks. Sometimes this is done for you. Sometimes you need to bring in a ruler or use your fingers. Every peak should be a whole integer. At this point, make some basic functional group assignments in the margin of your test, or on some scrap paper. Step 4. Break down the peak splitting to determine how many neighbors each proton has. If a peak is split in 3, it has 2 equal neighbors. With 3 neighbors, a quartet is formed, and so on. The number of neighbors is always 1 less than the number of peak subunits. Now, it's time to turn back to your scrap paper and build on your earlier structural fragments. Make small 2 to 3 carbon chains and simple ring systems. For step 5, turn to the carbon spectra and group the peaks into likely functional groups, as was done with the protons. Look for things that enforce or tear down your current structure fragments. Step 6. If you have an IR, look for key peaks. Absorbances just above 3000 inverse centimeters suggest alkenes and alkynes, while a strong band around 3400 indicates an alcohol or an amine. In this spectra, we have a strong band at 1700, suggesting either a ketone or an ester. Step 7. Put your molecular fragments together using your notes. Beware the additive effects of de-shielding neighbors. A benzylic hydrogen that's next to an ether will be more upfield than if it had only one neighbor. Carbon shifts are less affected by this and can be used to confirm your gut instinct. When you've got something plausible, move on to the next step. Here, you want to try and tear down the structure you just built. Does the molecular formula match what was given? Are the protons and carbon shifts where you'd expect them to be? Most importantly, does the coupling of the protons match the number of neighbors in your structure? If not, build a new structure and repeat the testing. Keep this up until everything in your structure matches your spectra, and you'll always get the right answer. And that's the algorithm. You can find it written down in the description box below, or at the Chemtips blog. Good luck!